Hello everyone, it's Mr. Younger again. I'm here to solve a conduction problem for my physics students. Let me start by sharing my iPad screen. All right, now everybody can see my iPad screen, and the question is as follows. In Chicago, there are many buildings that are clad with clear glass walls. One such building has a window made of 5.00 millimeter thick glass that is 3.00 meters tall and 6.00 meters wide. On a very windy day, that thin layer of air outside the window is at 0.00 degrees Celsius, while the layer just inside the window is 3.00 degrees Celsius. In joules per second, how much heat is allowed out of the building? Now, in this case, we're talking about how much heat's being lost by a window, and your textbook, as do all textbooks, discusses basically how there's always a slight layer of air just outside and just inside of any window pane, and that actually makes your windows a little more good at not letting heat in and out. That being said, on a windy day, the outdoor one can completely disappear, and that's what I'm trying to uh, allude to in this particular problem. And the one inside is often very close to the one outside, and normally it's not affected by wind, but still, I wanted you to consider that it was probably a cold enough day and enough traffic coming in and out of the building that the air next to the window was also quite cold. Let's get started. I'm going to go ahead and begin by writing out solution. So what we're using here is the conduction equation, and that basically says that a amount of heat Q will be conducted through the glass pane every amount of time t, such that Q over T is equal to K, and that, of course, is a property of the glass specifically. So we're actually looking at what's called the thermal conductivity, K. It's also proportional to the area, and in this case, we mean the cross-sectional area is sort of like the width and the area specifically of the hole through which the heat is supposed to transfer. And then the difference in temperatures, T1 minus T2, divided by the thickness of the material, which is L. And in fact, that last quantity in parentheses is normally called the temperature gradient. So that's our formula. Q over T is equal to the thermal conductivity times the cross-sectional area times the temperature gradient across the window. We also know specifically for the glass, the thermal conductivity is 0.84. And of course, you can make out that the units must be joules per second from the Q over T. So I'll write joules per second. But then we also got an A in the top and an L in the bottom. So I've got to cancel out a meter on top. So there'll be a meter in the bottom as well. And I've also got to cancel out a temperature difference in the numerator. And we normally indicate a temperature difference by C degrees instead of degrees C. So we have that quantity. We also are told the dimensions of the window, and that gives us an area equal to, in this case, it's going to be 3.00 meters times 6.00 meters. That's 3 sig figs times 3 sig figs, so that should spit out 3 sig figs, and the units are square meters. So now all we have to do is do the calculation, and proceed as follows. So Q over T is going to equal K times A times T1 minus T2 over L. And you have to remember, according to the second law of thermodynamics, heat flows spontaneously from a warm body to a cold body. So that should indicate which temperature you call T1 and T2. In this case, I'm just trying to make sure I get a positive quantity because I only care about the amount of heat, and I'm not really thinking too much about which direction it's going. But hopefully, everybody realizes that since the inside of the building is warmer than the outside of the building on an extremely cold day, clearly heat should be flowing from the outside to the from the inside to the outside. So I'm going to go on just to get a positive number. It's going to be 0.84 joules second meters Celsius degrees times the area, which is 18.0 square meters, times, in this case, 3.00 degrees Celsius minus 0.00 degrees Celsius. I obviously made up these temperature values specifically so I could try to get 3 sig figs from everything. Of course, the thermal coefficient or the thermal conductivity is only 2 sig figs, so that sort of messes me up. Notice also that I have to use everything in the typical SI base units, which if it was mass, that would be kilogram, but everything else shouldn't have a prefix on it. In this case, it's 5 millimeters, and that is the equivalent of 0.00500 meters. Notice I did have 5 millimeters to 3 sig figs as well. So now that I calculate this, all I have to do is take 0.84 times 18.0 times 3.00 minus 0.00 is 3.00, and then I'm going to divide that all by 0.005. And when I do that, I think I got everything. I got 0.84 times, hold on, 0.84 times 18 times 3 divided by 0.005, and that gives me 9,072 joules per second, which also means a watt, by the way. And because the 0.84 was only 2 sig figs, the 7 and the 2 cannot be sig figs. So in fact, this window is actually allowing almost 1,000 watts to be wasted. So this is basically the amount of heat as, let's say, 90 100 watt light bulbs. So 90 100 watt light bulbs are just putting out so much heat, yet all of that amount of heat is exactly how much is going through this one window. So obviously, there's a very good reason to have, for instance, double pane windows so that you can secure that inner layer of gas between the two panes, and you still have the outer layer of air outside of the pane and the inner layer of air on the inside of the pane. So hopefully that gives you some idea of how to use the equation. Actually, in your Pearson homework, you'll see that Giancoli takes a good deal of time trying to make sure you understand exactly what this equation means. So pay close attention to those long-worded multi-step problems in the homework set. But that should be it. I hope that helps. Have a good day. Bye-bye.